Hello, welcome to first class of physics. Okay, so I know you've had a few weeks. I'm gonna take these off. A few weeks to start, and most of this is going to be review, but that's okay. I want to make sure you've got this drilled in your head, because if you don't have the basics of physics, you can't move on. So we're going to talk about some terms today. We're talking about acceleration, velocity, displacement, scalar quantities, vector quantities, all of that stuff. Okay, so first off, let's talk about how we measure physics. So I'm going to give you some terms. So if I star a term, if I put a star beside a word, that means that it's important and that you can make, we'll talk about points hopefully today in class, but you can make note cards for points. Okay, so let me get my parameters working right. You can see me there, you can see me all the way to here. Beautiful. Okay, so first off, let's talk about what a scalar quantity is. Okay, once again, you probably have heard this stuff, and that's okay. So a scalar quantity. A scalar quantity is a measurement with a singular quantity without direction. Okay, so a scalar quantity is a measurement with a singular quantity without direction. Okay, so in other words, this is what you should see in this word. You should see scale. Okay, so these are things you would literally measure. So temperature, 45 degrees if you have a thermometer, or you have a literal scale that says 85 grams, or a stopwatch that says 5 seconds. So it literally just gives you an amount. It doesn't give you the direction of the amount. In other words, they're not going, it's not 65 degrees increasing at a rate of 3 degrees a minute. Okay, that would not be scalar. We're going to talk about what that is in a second. So when you see scalar, think scale. Okay, think of a scale. All right, pause it if you don't got it. Moving on. Okay, so the next quantity we're going to talk about is a vector quantity. Okay, now a vector quantity is the opposite in that it includes quantity. That includes direction. So what did I write? A measurement? Yeah. Measurement, a single measurement, that's what I put. A single measurement, that's what I'm putting. A single measurement with direction. That's what I should have put with the other one. With direction. Now, that direction does not have to be a speed or a time or anything like that. It can be, I walked, for instance, okay, I walked 10 meters north, okay? And I'll write north. 10 meters north. So, what's the distance? Well, the distance is 10 meters. Do I have direction? Yes, I went north. Okay. Even if I put the temperature went up to 65 degrees, that would technically be a vector quantity. If it has any form of direction, it's a vector quantity. Okay. And this should be given because you know what a vector is, even though I'm getting ready to define it. Okay. Vector, excuse me, is a well, let's do this. I'll leave a vector alone. You should know what a vector is. It has direction and quantity. Okay. That's why it's a vector quantity. Okay, so now we're going to talk about displacement. So displacement, you should also know. Okay. Now all these come together, and I'll talk about how they come together as we move on. But right now you need to know the words. Displacement. Displacement, okay, is distance and direction between two positions. Distance and direction between two points. Okay, now What's important is, I know you've probably seen this. It's actually a lowercase d. Velocities are changing distance over time. This d, it does not stand for distance, okay? Anytime you see a d in physics, it does not stand for distance, it stands for displacement. The reason being is we don't want just the distance, we want the direction in which we moved, okay? So the symbol is just a lowercase d, okay? Write that down. So displacement is the distance and direction between 2 points. Remember, you need both of those in order for it to be displacement. Okay? In other words, if I had, sorry.
Todd, could you come to the office, please?
If you had, Susie Q and John are 50 meters apart. Okay? You have a distance, you don't have a direction. But if you said Susie Q is 10 meters north of John, now you have displacement. Okay, that's the difference. Alright, moving on. So now that we know about displacement, we're going to talk about how that applies to bigger stuff in physics. Now I have notes above you, that's why I am changing this page above you. Okay, so before we get into that though, let's talk about what this symbol means. Okay, first off, what is that? Yeah, it's a triangle, I know. But it is a delta, a lowercase delta in the Greek alphabet. Now we use Greek letters all the time in math. And since physics is very math related, you're going to see a bunch of them. You may see delta, you may see another one you might see is sigma, okay? And they all have different meanings. A delta means, let me give you an exact definition of a delta. Change in quantity, that's what it is. Change in quantity, let's put that down. Change in quantity. And I'll give you sigma, I don't know if we'll use it much, but I'll give it to you. It means the sum of. Okay? Looks like a weird E. And this isn't rounded off, it's squared off at the top. Like that. Okay, if you didn't get it, pause it right now. Okay, so what we're going to do is, I'm going to leave this change in quantity so you remember that up top. So if I have this, I have delta D. That means what? The change in what? No, not distance, displacement. Okay? Now, for all intents and purposes, if it helps you to think of distance, you know, that's okay. Because that's more or less what it is. We have direction if we were talking about anything in the change in D because we know it's moving in a certain direction. Anyway, so what if I give you delta T? What do you think T stands for? Okay, change in time. Now, we just wrote the formula for velocity. Now, it's not just velocity, okay? This is average velocity. This formula is average velocity. The reason being is average velocity. Okay. Let's write that down. Okay, make sure I'm covering everything. Looks good to me. Okay, so that's your average velocity. The reason that is an average is because you take, in order to have a change in, you need an initial value and a final value. So this is the same as doing, and this is how you will, this will be your notation. Okay, this is also a note card, and so is this, and so is sigma. But okay, I keep forgetting to start things. So this is really d1, so your initial distance or your final distance minus your initial displacement. I'm gonna keep saying distance. Okay, over your final time minus your initial time. Okay, because you're taking, if it's the average, you take and combine the beginning and the end and figure out what we're doing over the course of the entire thing. Okay, so that is what this means. That's average velocity. So, however, if I give you this, okay, I'm going to get rid of my delta now, is instantaneous velocity. And I'm kind of flying through this because I know you've had a lot of it. Instantaneous velocity. And instantaneous velocity is velocity in an instant, okay? It's in a single moment of time. So average velocity is over a course of time, so t0 to t1, okay? Instantaneous velocity is at that very, very millisecond. Okay, so instantaneous velocity, there's just no deltas, okay? So it's just distance over time at that moment. So your symbol for instantaneous velocity would just be v, whereas for average velocity, I should have wrote this, I'm sorry. Your average velocity is v of the line over, because that line means average. Okay. Makes sense? I hope so. If I tell you that a car is moving at 3 meters per second, okay, then would that be a average velocity or initial velocity or instantaneous velocity? Instantaneous velocity. I didn't give you a length of time, and I didn't give you a beginning velocity or beginning distance and end distance. Okay? So, hope that makes sense. We're going to move on. Now, seeing that in average velocity is the change in distance over time, we're going to keep stepping up, okay, to find acceleration. So, I want you to see this. The change in displacement over change in time is equal to the average velocity. Okay. Now, the change in velocity over time is equal to your average acceleration. Now, once again, what does that delta mean? Acceleration. I'm misspelled acceleration. You'll learn very quickly that I cannot spell. Okay, so what's the delta mean? It means an initial or final minus an initial, right? So you've got V1 minus V0. Final, initial. 0 will always be your initial quantity. Okay. Over, what's my initial time? T0, good. My final time is T1. Now, could I have more than 2 T's? Yes, I could be at time 0, at time 5, at time 6, at time 7 seconds. You know, I can have all these different times, and each of those will be labeled differently. That's why we have these labels, so that we understand. When we get in the upper physics, you're going to have definitely more than just the 2. Okay, so do we see how we are, these are so similar? Okay. They are very, very similar, which is good for us, okay? But it's also confusing because we're going to get mixed up. Because you're going to make sure you're working either with displacement or if you're working with velocity. Okay, because if you're working with velocity, you're looking for an average acceleration. If you're working for displacement, you're looking for average velocity. Okay, so acceleration. So if this is, how can I explain this? Its velocity is change over time, right? Is distance over time. So velocity. So let's do this. This is how I'm going to explain this. Get rid of all that. Now, what is velocity again? Velocity. So I'm going to expand this. Is d over t, right? Over t is what we have. D over t over t. So what that means is, this is d over t squared. Does that make sense? I hope that makes sense. This is simply d over t. So it's over your time squared. That's why acceleration is you have to be either increasing or decreasing constantly. Okay? That's why we have time. Because when you square time, you get this curve. And I showed you this in class last week. Okay? Whereas velocity, you're going to get straight lines. Okay? That's where the t and the t squared affect it. Alright, so I probably didn't make any sense. And if I didn't, just yell at me and we'll figure it out. Okay, so we've got distance, velocity. I'm at 15 minutes. I'm going to take a break right there. We're going to stop this video. Let me make sure I got through everything I wanted to. I wanted to get all the way through. Oh, let's do a problem, okay? And then I'll leave you alone. So here's the problem. It's on page 59 if you want to read it. It's one that I think you probably have done. So a car is moving at 25 meters per second. Okay, if you've done this problem, great. If you want to pause the video and try it on your own, and then come back and see how to do it, that's even better because then it'll give you a refresher and make sure you know what you're doing. Okay, car's moving at 25 meters per second. Kid runs in the road. Kid enters road. So car hits the brakes. So it slows at a rate of 8.5 meters per second squared. 8.5 meters per second squared. Now, it wants to know what's the total distance to stop. Okay? Now, we need to figure out, this is what I want you to do for every single physics problem you do. And you can hate me for it, but I want to see this because it'll help you piece everything together. You've got to put down all of your knowns. So what do you know? And then I want you to put here what you're trying to find. So first off, it's always easier for me to figure out what I'm trying to find because it's usually the last sentence in the problem. So what I'm trying to find right here, total distance. Okay? Trying to find total distance. Now what I do when I do this is I don't erase it because you can't see it anymore, but I mark through it. So total distance when I'm first working on this problem. I'm trying to find total distance. So I will mark through that so that, I mean, I can still read it, but I'm not looking at it anymore. Now what do I know? What is my initial displacement? What is D1? Okay. Now, did I put a... Yes, I forgot something. I'm sorry. It takes the driver 0.4, yes, seconds to react. Okay. Sorry. So at D1, our distance, right now, I am driving down the road. Okay. From the instance that I see the kid, that's where we're worried about the problem. We're not worried about if I've been driving for 3 hours and I've covered 300 miles. We don't care about that. We care about at D1. So D1, or we're going to say that is 0. Okay. What does D1 represent? I'm sorry. What does D1 represent? That is our displacement, right? So that's from our initial time of hitting the brakes. Okay, that's where we're starting. Okay, so now, what is our velocity at D1? So before we think, okay, what's our velocity? Before I see the kid, before I realize anything, my V1 is 25 meters per second. So now that I wrote that down, what do? Mark through it, okay? Now, what is my, let's see, what is my acceleration? So this is, first of all, let's do this. I want to make this easier for you, okay? Here's my pathway, right? I want to put 0, okay? So that's my time. This is my t, okay? This is position 1, so I've got a car here at position 1. Okay, then I have position 2. Now I want you to figure out what the difference in these two positions are. And then I'm going to have my position 3. Okay, those are my little cars. So here, so in this distance 1, I haven't seen anything, I'm just driving. Then I react. And then I brake. Okay. Now, this is position 1 of car, position 2 of car, position 3 of car. So my acceleration has to do with a velocity over a time, right? Velocity over a time. So this is my acceleration from 1 to 2. So this is how you write this. A1 to 2 is what? From here to here. Am I increasing or decreasing speed at all? No, I'm hanging out at 25 meters per second. So my acceleration is 0. Okay? Now from the next points, so A2 to 3, my acceleration is what? 8.5 meters per second squared. Now, if I am braking, what does that mean? That means that it's going to be negative because I'm slowing down. Okay? So now we're getting there. We've almost got everything. Now, from T0 to T1, okay, at T1, 0 time is taking place, right? So we're not worried about, or from right here, there's no time taking place. At T, from here to here, so 0, T1, T2, okay? At T1, exactly 0.4 seconds has taken place. I'm trying to make sure I'm doing this the same as the book. No, they're doing stuff weird. I'm going to keep moving on now. Okay, my velocity, what is my final velocity? So V3, so right here, at 3. My final velocity is going to be 0. This T1 is right here, so let's mark that out, I forgot. Okay, marked out my acceleration. And my final velocity is 0. So now, the way I'm going to solve this problem is this. I'm going to take I need to figure out the distance from 0 to here and from here to here. So I'm going to have two distances, or displacements. And I've got to add up. So I'm going to put D1, D2. So my total displacement is D1 plus D2. Okay? And I don't know why the book put D1. I'm going to put D0 there because that makes more sense to me. Okay, because that's your initial velocity. Same here. So, how am I going to figure out from here to here? Well, how long did I go, how much time passed between time 0 and time 1? So what is my reaction time? It's 0.4 seconds. So I got 0.4. Now what am I going during that speed? Okay, I haven't hit the brakes yet because my brain has not reacted and I've not hit the brakes. So I've gone 25 meters per second times 25 meters per second, right? So when I multiply 0.4s times 25 meters per second, what am I going to get? The reason that this gives you a displacement is because your s's cancel out. Wow, this is a long video. I'm sorry. Okay, so you get 0.4 times 25 is going to give you a whole meter, right? All right, 0.4 times 25. Looks good to me. We might give you 4/10 of that. So 1/10 is 0.2, 2.5. So it's 10 meters. Okay, 10 meters per second, because there's a second here, over seconds. Now what happens to your seconds? They cancel out. That is why a time times the velocity will always give you a displacement. So D1 equals 10. So let's replace that with 10 meters. Now for D2, it's a little more tricky, right? Because now we're dealing with acceleration. Okay, and we don't know a time. So we need to figure out our average acceleration. So what I'm going to do is I'm going to divide my velocity by my acceleration.
Aaron Johnson, please report to the front office. Aaron Johnson, please report to the front office.
Divided by 8.5 per second. Okay. Once again, I'm going to show you how this cancels out and works. So when you multiply fractions, okay, because this is a fraction, right? Or when you divide, this is 25 over 1 divided by 8.5 over 1, technically. When you divide fractions, you flip, change, flip, right? So you do 25 over 1. Can you see all of this? I hope so. It's getting close. I want to put it over here. You get 25 over 1, okay, meters per second, times 1 over 8.5. Keep, change, yes, flip that one. Okay, so now, and this is, I flip this as well. Okay, so now when I multiply, 25 times 1 is 25. Okay, I still have to divide, so 25 over 8.5. But I'm going to get seconds per second over meters per second. So now, oh, and I get a meters on top too. So now what happens is my meters cancel out, my seconds cancel out, and I'm left with a second. So this is going to give me a time, right? Great. So now I have a time that I can plug into my acceleration and figure out what it's going to be. Or my velocity, I'm sorry. So now, holy crap, this has been a long problem. You know what I'm going to do? I'm going to stop right there. I'm going to let you figure out the rest of it. Don't forget you got to divide this. You're in a number, and it's going to give you a time. I know that's weird for teachers to do, to mark through 3/4 of the problem. But you've already done this problem, and I want to make sure you get to the end. So once you get here, I want to see if you can solve it. Because you've still got to find D2 and add them together. It's been a long video. I'm sorry. Hopefully that this all has made sense.